Have you ever looked up at the night sky and wondered what secrets lie hidden in the darkness? The universe is vast. It is filled with countless stars and galaxies. Many of these are just too far away for us to see, even with our most powerful telescopes. But what if I told you that the universe has its own natural magnifying glass, a way to bring these distant hidden objects into view? This is not science fiction. This is a real phenomenon known as gravitational lensing. It is actually one of the most incredible tools we have to explore the cosmos. It allows us to peer deeper into space and further back in time than we ever thought possible. To understand gravitational lensing, we must first change how we think about gravity. For centuries, we saw gravity as a force, an invisible string pulling objects towards each other, as described by Isaac Newton. But Albert Einstein, with his theory of general relativity, offered a completely different and more profound explanation. He asked us to imagine that space and time are not separate things. Instead, they are woven together into a single, four-dimensional fabric he called space-time. This fabric is not just a passive backdrop for the universe, it is an active participant in cosmic events. Einstein's great insight was that massive objects do not just exert a force, they actually bend and curve the fabric of space-time around them. Think of it like placing a heavy cannonball onto a trampoline. The cannonball creates a deep well in the fabric. This is precisely what stars, planets, and entire galaxies do to space-time. The more massive the object, the deeper the curve it creates. This idea, that gravity could bend light, was a staggering prediction. In 1919, during a total solar eclipse, the astronomer Sir Arthur Eddington set out to test it. He photographed the stars near the sun. His observations showed that the positions of the stars appeared slightly shifted. Their light had indeed been bent as it passed by the sun's immense gravitational field. It was not until 1979 that astronomers found the first concrete evidence. They discovered an object called the twin quasar. It appeared to be two identical quasars sitting very close to each other in the sky. But further study revealed something extraordinary. It was not two separate objects at all. It was a single quasar, whose light had been split into two images by the gravity of a massive galaxy lying in between. This discovery was a watershed moment. It transformed gravitational lensing from a theoretical concept into a practical tool for observing the universe. Suddenly, astronomers had a new window to look through. Gravitational lensing is not a one-size-fits-all phenomenon. Strong gravitational lensing is the most dramatic and visually stunning type. We might see double images like the twin quasar, or even four images arranged in a cross shape, famously known as an Einstein cross. Weak gravitational lensing is far more common, but also much more subtle and difficult to detect. Instead, it causes a slight, coherent distortion in the shapes of background galaxies. By measuring these tiny distortions across a large area of the sky, astronomers can map the distribution of mass, including dark matter. Finally, there is microlensing. This occurs when the lensing object is much smaller, such as a single star or even a planet passing in front of a more distant star. This powerful technique is one of the primary ways we search for exoplanets and lone, wandering stars within our own galaxy. One of the greatest mysteries in modern cosmology is dark matter. We know it is out there. We can see its gravitational effects on the stars and gas within galaxies. It is the invisible glue that holds them together, preventing them from flying apart. But we cannot see it directly. It does not emit, absorb, or reflect any light. So how can we possibly study something that is completely invisible? Gravitational lensing provides a remarkable answer. It allows us to weigh the universe, including all the matter we cannot see. The power of gravitational lensing lies in its democratic treatment of matter. Gravity, as described by Einstein, is a response to mass, regardless of what that mass is made of. Using the technique of weak lensing, we can create detailed maps. These maps reveal vast, ghostly halos of dark matter surrounding galaxies and filling the space within clusters. This has enabled astronomers to perform a cosmic audit, weighing galaxy clusters and comparing the mass indicated by lensing with the mass they can see in stars and gas. One of the most exciting applications of gravitational lensing is its ability to act as a cosmic time machine. When we look at distant objects in space, we're also looking back in time. Seeing a galaxy that is 13 billion light-years away means we are seeing it as it was 13 billion years ago. when the universe was still in its infancy. The challenge is that these incredibly distant galaxies are also incredibly faint. This is where gravitational lensing comes to our aid. By using massive galaxy clusters as natural magnifying glasses, the cluster's gravity boosts the faint light from a background galaxy, making it bright enough to be detected and analyzed. This technique has led to the discovery of some of the most distant objects ever observed. One of the most remarkable discoveries enabled by lensing was a star nicknamed Earendel, the Old English word for morning star, found in 2022 using the Hubble Space Telescope. Earendel is the most distant individual star ever seen. Its light took 12.9 billion years to reach us. This gave us an unprecedented glimpse into a single star from the dawn of the universe. Gravitational lensing doesn't just operate on the grand scale of galaxies and clusters, it also works on the much smaller scale of individual stars and planets. This is the realm of gravitational microlensing, a clever technique that has become a powerful tool in the hunt for planets outside our solar system, known as exoplanets. Now here is where it gets really clever. If the foreground lensing star also has a planet orbiting it, that planet has its own small gravitational field. This appears as a short, sharp spike or blip on top of the smooth, brightening curve of the main microlensing event. Detecting this tiny blip is the telltale signature of an exoplanet. This technique has been remarkably successful. It has also led to the discovery of rogue planets, worlds that have been ejected from their original solar systems. These planets are almost impossible to detect by any other means. Microlensing provides a unique window into these hidden populations, revealing that the cosmos is filled with worlds far beyond our own. One of the most fundamental questions in cosmology is determining the rate at which our universe is expanding. This value, known as the Hubble constant. However, gravitational lensing provides a completely independent and unique way to measure this cosmic expansion. It relies on a time delay effect that occurs in strongly lensed systems. This method works with systems where a background object, typically a bright and variable quasar, is lensed into multiple images by a foreground galaxy. Since quasars are not constant in brightness but flicker and vary over time, we can measure this time delay directly. By monitoring the lensed images, astronomers wait for a flicker in one image. This technique, known as time delay cosmography, provides a one-step measurement of the universe's expansion rate that is completely independent of other methods. Gravitational lensing offers a powerful, alternative perspective to help resolve this Hubble tension, one of the most significant challenges in cosmology today. Despite the challenges, the future of gravitational lensing is incredibly bright. We are entering a golden age of observational cosmology. Leading the charge from the ground is the Vera C. Rubin Observatory, currently under construction in Chile. In space, the European Space Agency's Euclid mission is already underway. When it begins its decade-long legacy survey of space and time, it will image the entire southern sky every few nights. The survey will catalog billions of galaxies. By measuring their subtle distortions, it will create a three-dimensional map of the dark matter distribution, tracking how it has evolved over the past 10 billion years. We will be able to test our cosmological models with unprecedented rigor, search for tiny deviations from general relativity, and perhaps even uncover the nature of the dark matter particle itself. By overcoming the challenges of today, the next generation of astronomers will use gravitational lensing to create the sharpest and most detailed picture of our universe yet. We have journeyed across billions of light years, from Einstein's brilliant mind to the very edge of the observable universe. We have seen how gravity, far from being a simple pull, is woven into the very fabric of space-time, a fabric that can be bent and warped by the presence of mass. This warping gives rise to one of the most elegant and powerful phenomena in all of nature, gravitational lensing. It is the universe's own telescope, a cosmic magnifying glass that allows us to see what would otherwise remain forever hidden. It is a testament to the profound beauty and ingenuity of the physical laws that govern our cosmos. What began as a curious prediction of a revolutionary theory has become one of the cornerstones of modern astronomy. It has given us the first concrete evidence for dark matter. It has acted as a time machine, boosting the faint light from the dawn of creation, revealing the very first stars and galaxies as they ignited in the primordial darkness. It has even shown us new worlds, detecting planets orbiting distant stars through fleeting flickers of magnified light. This cosmic mirage is far more than an illusion. It is a source of deep truth about our universe. By studying the distorted arcs, the ghostly rings, and the multiple images created by lensing, we unlock fundamental secrets. Ultimately, gravitational lensing changes our perspective. It reminds us that the universe is not just a static collection of objects to be observed, but a dynamic and interconnected system. It is a beautiful demonstration of how the fundamental laws of physics can create phenomena of spectacular complexity and utility. The path of light may be bent, but it leads us ever closer to the truth.